Okay, the next reaction we're going to look at is called the Michael addition. This is a conjugate addition reaction, and what that means is that our nucleophile, just like we saw in the previous video, is going to attack the beta carbon on an alpha-beta unsaturated carbonyl. Another way of describing this is a 1,4 addition reaction. So we're going to do this conjugate addition. The nucleophile is going to attack the beta carbon, but in order to do that, we need to use a relatively weak nucleophile. So we're going to be using typically a highly resonance stabilized carbanion, meaning the carbon in this is going to act as the nucleophile. And because it's highly resonance stabilized, it's going to be somewhat weak as a nucleophile. It's not going to be as aggressive as something like a Grignard reagent. So let's take a look at one of these highly resonance stabilized carbanions. And I'll show you a classic example. Let's say we have this 1,3 diketone, right? This diketone has 2 alpha protons in between the carbonyls. So if we were to treat this with a base, like hydroxide, it would quite easily grab one of these alpha protons and create an enolate that is really resonance stabilized, right? Because this negative charge has the option of delocalizing up to that oxygen, or it could delocalize up to the other oxygen. So it's very stabilized. If you try to do this with a regular enolate, it's kind of in between strong and weak, and you tend to get a mixture of 1,2 and 1,4 addition products. Versus this one, it's so resonance stabilized, it's going to be incredibly weak. So let's make a note on that. It's a highly resonance stabilized, which means it's going to be a weak nucleophile. All right, so let's see what happens if we treat this with a conjugated aldehyde. So the conjugated aldehyde that I'm going to use is going to be this one. And like we said before, the alpha position is going to be attached to that CO double bond, and the beta position is going to be one further away. So when this attacks, it's going to prefer to attack that beta position, and we're going to kick electrons all the way up to that oxygen. So let's draw our intermediate. In this intermediate, what we've done is we've created a new carbon-carbon bond, and we've actually created a new enolate. And this is somewhat unique, right? Because I'm actually going to slide this down a little bit. Because if we think about this product that we just made, this has a resonance structure where we can delocalize electrons back to that carbon. So let's go ahead and draw both resonance structures. Oops. Should have a double bond here and a negative charge down there. So we've got this resonance stabilized enolate after this addition reaction. All right, now in our next step, all we need to do is to react this with our conjugate acid from step 1, which is water. And this negative charge can grab this proton and kick off hydroxide. And when we do this, we're able to get a neutral product. So if we think about this, this was our aldehyde that we added into. This was our original starting material. And we've added to the beta position, not the alpha position, on our original alpha-beta unsaturated aldehyde. It's kind of a unique reaction. We've seen a lot of alpha alkylation, but this allows us to install something off of the beta position rather than the alpha position. All right, I wanted to show you a bunch of these resonance stabilized carbanions. So let's do some examples of highly stabilized carbanions. The common name for these are called Michael donors. And there's a variety of these that tend to show up over and over again. This won't be an exhaustive list, but it's a pretty good one. A good example would be something where you have a negative charge between two ketones, right? So this is similar to the enolate I showed above, where that negative charge can be delocalized to either oxygen. You can also have the diethylmalonate conjugate base, where you'd have a negative charge there. So this has two esters. Or you could have the ethyl acetoacetate conjugate base, so half ester, half ketone. Same idea though, that negative charge can be delocalized across two oxygens. Another one, it's a little bit different, would be if you have a nitrile. And this is unique because not only can we move this negative charge up to that oxygen, but we can also move it to that nitrogen, right? So this, again, is highly resonance stabilized. All right, another one is a little bit different because we only have really one major resonance pathway, but that's okay. And that's where we have a negative charge coming off of a carbon adjacent to a nitro group. And nitro groups, like I said in our electrophilic aromatic substitution chapter, they're really, really strong electron donors. So in this case, the fact that it's such a strong electron withdrawing group, not donor, means that it will pull that negative charge over to the oxygen, right? So this is highly resonance stabilized simply because it has that strong electron withdrawing group. All right, the next one that we've already seen is going to be the Gilman reagent, right? That's the lithium dialkyl cuprate. Now in this case, it's not necessarily resonance stabilized. It's more stabilized because the bond between carbon and copper isn't as polarized as with a Grignard reagent. So it's definitely like a mellowed out Grignard reagent. It's not going to be nearly as aggressive. All right, so let's take a look at a practice example. All right, and this one's going to be a little bit different. So what happens if we treat cyclohexanone with a strong base like LDA, that's lithium diisopropyl amide, followed by an alpha beta unsaturated aldehyde, looks like this, followed by water, or let's just use dilute acid. In this case, we have to ask ourselves, what product or products will we get out of this? Well, let's take a look at this, right? So we've got this, and we're going to treat this with LDA, a very strong base. So it's going to rip off one of those alpha protons, and we're going to form pretty much 100% enolate. Doesn't matter which side we form that negative charge on because it's symmetric, right? And when we go ahead and we look at this, it is resonance stabilized, but not highly resonance stabilized. So what does that mean? What does it mean if it's stabilized but not as stabilized as what we saw in these Michael donor examples? Well, the reality is it could do both, right? It could do conjugate addition or it could do the 1,2 addition. And in this case, it's typically going to favor 1,2 addition over 1,4 addition. So let's make a note of that. Favors 1,2 addition over 1,4 addition. All right, so let's do both of them. So in the next step, we've got our aldehyde. And whoops, and let's consider the 1,2 addition. And I'm going to use a green arrow for this. That just means that it would attack into that central carbonyl carbon. Right? And if that were to happen, we would get a product. Whoops, this oxygen will have a negative charge that looks like this. And then in our last step, we're just going to protonate that using some sort of weak acid. And this would be our major product. We would end up with an alcohol, and then the double bond would remain intact. So this is going to be our major product. So this isn't a Michael addition reaction. This is just a classic addition reaction to a carbonyl compound like we've seen previously. All right, let's take a look at what could happen if we do the other route. So for this one, I'm going to use a purple arrow. And I'm going to say, well, let's say that it attacks this carbon instead. And if that occurs, we're going to get a completely different product. We're going to get a product that looks like this. And then in our next step, we're going to protonate it. And in order to do this, we typically favor the keto form. So I'm just going to show this negative charge clamping down, grabbing that proton. And we might observe a little bit of this conjugate addition product where the aldehyde actually remains intact, and instead we added to the beta position. So this would be the minor product. All right, so it's kind of interesting. Usually we don't want to get a reaction mixture like this. So the question is, if this is such a problematic starting material, meaning it will react at either position, is there any trick or tool we can use to favor one of these products but not the other? And the answer is yes. There's actually a workaround, and I wanted to show you this really quick. This is called the Stork enamine synthesis. I like to call it the Stork enamine workaround. And what this does is it kind of lowers the nucleophilicity of the enolate. So what we do first, before we do the rest of our reaction, is we take our ketone and we react it with a secondary amine. And again, we're going to use a low pH system. Typically, this is a buffered system, so it's not just that you're dumping in tons of acid. And you try to remove water during the reaction. And when you do this, you're able to make the enamine that we covered in our aldehyde and ketone chapter, right? So this is an enamine. But enamines are kind of unique, right? Because if we think about it, this has a resonance structure where we can kick electrons onto that alpha carbon. However, this is going to be a fairly minor contributor because, as you can see, it's definitely not going to be happy with carbon bearing the majority of that negative charge. It would prefer to have that lone pair on nitrogen. But what it does mean is that this carbon has some sort of partial negative character, right? So this is going to be a weak nucleophile, because this is such a minor resonance contributor. And if it's a weak nucleophile, that means that it's going to favor conjugate addition. Okay, so in this next step, what we can do is take that same aldehyde from the previous example, and we can say, well, this time it's going to attack that beta position, kick up electrons all the way to that oxygen. All right, and now we end up with this product that essentially is acting as a Zwitter ion, right? So we've got a positive charge and we've got a negative charge. All right, in the next step, what we're going to do is we're going to essentially quench the reaction using dilute acid and water. And let's go ahead and draw the whole mechanism for this just as a bit of review. And in our next step, we're going to first take this enolate and turn it back into our ketone, right? So this will be step one, is to quench that half of the reaction. However, we still have this nitrogen with a positive charge to deal with. But that's okay, because we still have water floating around. And it looks a lot like an imine or an aluminium ion like we saw in our ketone and aldehyde chapter, which means that water can attack in and kick up electrons to that nitrogen. So if we do this, we're going to end up with a tetrahedral intermediate where water added in on one side, and then coming off the other position, we still have this nitrogen group. And like we've seen before, we can do these proton transfers. So I'm going to move this proton over to the nitrogen. I'm just going to write plus minus H plus. That's just usually done with water acting as a solvent, and because water can act as either an acid or a base, it can help do that proton transfer. And I'll move it over to my nitrogen. Now, if we think about this nitrogen over here is now a good leaving group because it's got that positive charge. And we also have this aldehyde over here. So in our next step, what we can do is we can kick off that leaving group. So we can kick this off. And like I said, this hydrogen just came from proton transfers using water as a solvent. I'm not going to show both of those steps, but let's show what happens when we kick off our leaving group. We're almost there. Now in our last step, this nitrogen, being the best base in solution, can grab this proton, and we can get to our final organic product where we've regenerated our ketone. So really what we did was just hydrolyze off our enamine that was originally installed in the first step. And when we do this, we also typically end up with our protonated amine salt, but this is the product that we really wanted to get at the start of this reaction. So it's a clever workaround for getting 1,4 addition when you don't have a very good Michael donor. So in order to do that, we just make something that looks like a good Michael donor by making an enamine. And that gives us this weak nucleophile that favors addition at the beta position. If you're going ahead and trying to do this with a regular enolate, meaning one that's not highly resonance stabilized, you're going to get a mixture of major and minor products, which isn't desirable. All right, good luck studying, and let me know if you have any questions.